All right, today we are diving into something that, on the surface, looks like a chemistry curriculum. But it's so much more than that. We're really looking at a blueprint for scientific thinking. It's a guide that shows us how we build knowledge from the absolute ground up, all the way from foundational rules to real world, life saving applications.
And this right here, this is the mission statement. This is the whole point. The goal isn't just to make students memorize formulas, it's to create problem solvers. And that mindset, well, that's absolutely critical in any applied science, but especially in a field like biomedical engineering, where every single calculation can have a pretty profound impact.
So here's our roadmap for today. I want you to think of it kind of like a funnel. We're going to start really broad, looking at the philosophy of how knowledge is even built in the first place. Then we'll narrow in on the fundamental particles and their rules. We'll get super focused on one critical technique, and then finally, we'll zoom right back out to see how that one skill powers some incredible real-world innovations.
Okay, let's get into it. First things first, we have to understand the architectural plan, right? How do you actually construct a mind that can think scientifically? It's definitely not about just stacking a bunch of facts on top of each other.
It's done using something called a spiral curriculum, and the idea is just brilliant in its simplicity. You don't just learn a concept once and, check it off the list. You revisit it again and again, but each time with more depth, more complexity. It's kind of like building scaffolding. You build a really strong base, then you add new layers, reinforcing the entire structure as you go higher and higher.
So now that we have the architectural plan, let's look at the foundational materials in our blueprint, the atoms themselves. I mean, every complex structure from a simple water molecule to an advanced biocompatible polymer, it's all built from this one starting point.
You know what's really interesting here? This timeline, it basically mirrors that spiral curriculum idea we just talked about. Our understanding of the atom wasn't some single aha discovery. Each model was a revolution built on the limitations of the last one, going from a simple philosophical idea of atoms all the way to our modern quantum mechanical view. And when it comes down to it, it all boils down to these three little particles. Protons, sure, they define the element's identity. But it's the arrangement of those outermost electrons that's what dictates its personality, how it will bond, how it will react, how it'll interact with the world. All the staggering complexity of material science really just emerges from the behavior of these electrons.
So, knowing what an atom is, that's step one. But the real power comes from being able to predict what millions of them will do. And for that, we need to understand the rules of engagement, the basic principles of chemical bonding.
And there are really two main ways this whole thing happens. You can think of it as giving and taking versus sharing. With ionic bonding, one atom literally transfers an electron to another. This creates charged particles that then attract, like tiny little magnets. But with covalent bonding, atoms share electrons, linking them together into really stable molecules. And that distinction, that's fundamental to creating materials with specific properties.
And this question right here is where the rubber really meets the road. This is what separates pure theory from application. Because in fields like biomedical engineering, close enough is never good enough. You need absolute, rock-solid precision. So how do you get there?
Well, this brings us to the narrowest point of our funnel. We're going to focus on one single, indispensable technique that is the absolute bedrock of quantitative chemistry, and that is stoichiometry.
Okay, that's the textbook definition. But a much better way to think about it is as the grammar of chemistry. It lets you read a chemical equation not just as some abstract statement, but as a precise recipe. It tells you exactly how much of each ingredient you need and exactly how much of the final product you're going to get.
And this is the process. It's a 5-step logical chain. The real key here is converting everything to this universal unit called the mole. You can just think of it as a standard batch size for atoms. It lets you compare apples to apples. So once you have your batch count, you use the ratio from your recipe, and then you just convert back to the measurement you actually need, like grams. It's methodical, it's repeatable, and it is so powerful.
And here's a perfect example of that power, pulled right from the curriculum. In the reaction that combines hydrogen and chlorine gas, stoichiometry lets you predict that if you start with exactly 100 milliliters of hydrogen, you will produce exactly 200 milliliters of hydrogen chloride gas. No guesswork, no estimating, just the precise, logical application of that 5-step process.
So, let's zoom back out. Let's widen the lens. We've drilled all the way down into this one specific skill. So, why does this single technique, taught in 10th grade, matters so much to someone who's designing the future of medicine?
Because the logic of stoichiometry is absolutely everywhere in biomedical engineering. I mean, think about synthesizing a new biomaterial for an implant. The exact ratio of your starting chemicals. That's what determines its final properties. Will it be strong and rigid or flexible and porous? That's a stoichiometry calculation. Or think about drug dosage. Making sure a patient gets the precise amount of an active ingredient in an IV drip, that comes down to the same fundamental how much calculation. From creating stable buffer solutions for cell cultures to designing diagnostic tests that measure things in a blood sample, every single one of these advanced applications is built on that simple grade 10 blueprint.
So the real takeaway here is this. Innovation isn't just about the flashy, cutting-edge tools. It's about having a deep, deep mastery of the fundamental logic that underpins everything. The most revolutionary creations, they're built on the most elegant and timeless blueprints. So the final question is, what blueprint are you building on?